Hello, my name is Mike Yoon, and today I'm going to be presenting about my implementation of GANs and time series data. A little disclaimer before the real presentation. There's a lot to explain, but I'm going to try to condense it as much as possible, in order to fit the 5 through 8 minutes um presentation limit. So yeah. So the problem with this data, with the motivation problem. So we have time series data, and what is time series data? It's basically a continuous data over time, and it has temporal dynamics, which means, in other words, like changes over time, and it has sequential dependencies where um the value of a current event um depends on the past values, and because of these characteristics, it is hard to make a very like a linear model, like a very like a equation or formula to really characterize this model. Maybe use it for your series, but yeah, but in order to forecast or make a prediction model, we implemented a hidden Markov model, and then use those outputs of those state posterior labels in as inputs to our GAN, and then from the GAN we generated new values, prediction values. Uh, so what is the data that we were working with is time series data. Very noisy. Um, Everyone knows what it is, I guess, and yeah, very not niche. So this is our overall model. So I made a visualization of my model. So we have our sequence here, and we can put our sequence, put in our states, get our states, probabilities, and from the state probabilities we can get the joint probability, and then with the joint probability we put that into the random very the as inputs to the GAN, and then from the GAN we get the new data. Uh, so how I approach the model: first we normalize the data uh, with the mean zero. This is just like of electro zero, just one channel right here. Yeah, so it's 19 dimensional, multi-dimensional right here, as you can see. Um, and we because the data point we used actually just in our training data, it's 31,000 points just in our training data. So I averaged those the normalized values by 100 points, and then we got these windows. Looks very compressed, but still it's very like still kind of like characteristic. Very very yeah. So now about our Gaussian HMM. So I implemented this, and we can see that there are three states. I assume three states. And I got the high state one. It shows like the state with like the higher range of frequencies. State two with the lower range. State zero with like the medium range. And use these values as context. These probability values as context. And yeah, this shows convergence over just 40 iterations of the model. And this is our overall structure. Just got these and values, the noise, our original sequence, and then our gamma values or the state posterior probabilities, and then flan concatenated, and then put into the generator, and the generator generates a value, and then that fake value which is known right here is put into the discriminator and is output, and the discriminator determines if it's fake or real, and then it's trains the generator again and generates new value, put in the discriminator and the discriminator. Uh, so it's kind of like a loop again. Like the generator tries to fool the discriminator. So this is the formulas, uh, and this is how the loss value of the discriminator generator was trained. So we can see the loss value of the generator is basically, uh, as we can see, the discriminator putting uh, differentiating over the fake value and the which is x hat, and then we try to label that as 1 in order to fool the discriminator into thinking that's the real value. And then we took the mean squared error and compared it against the fake value with the real values right here. And we can see this is the result of our model. We can see adversarial loss and generator loss, discriminator loss. Discriminator loss is basically the loss of against the real and the fake, so that's why it's like 1.43. And we can see like the values stay consistent, never really like converges, but the mean squared error, it converges near 0, as we can see here. And this is our code. So it's basically the generator discriminator is like just a multi-layer perceptron. Well, we can see it has like 2 hidden states here, and it has 3. So this was the outcome. So basically, how we did it was how I did it was there's 30 steps sequence, and I predicted the next one and tested if the next value against the generator value, and just kept doing that for 1 step at a time. And this is just predicting for multi-steps, just like 50 steps. Just took a batch of like the past values and just predicted. And we can see like it converges to the normalized EEG, to the normalized mean value. And the reason why this happens is mainly because of the fact that we use a mean squared error, and so the data wants to like converge to the mean squared error. So in other words, the mean squared error loss function is actually much more powerful than the generator loss and the discriminator loss functions. So that's why it converges to the mean. So in the future, I could probably improve this by trying to make like a recurrent neural network based generator, make a stronger generator, and probably do like different regularization techniques. Yeah. And so overall, the model behaves very deterministically, like a regression model. And you can see that the noise is that we inputted to our generator is largely ignored because by the mean squared error. And yeah, that is it. Thank you for listening to this presentation.